Welcome to Waves. We're going to start with describing what a wave is. It's really described as a disturbance that travels through a medium from one location to another. In this case, it's actually an energy transfer phenomena. So as your disturbance moves through a medium from one particle to the next particle, the energy is being transferred from one end of the medium to the other. And this is an example of what we looked at when we're looking in charge and energy of electricity or electromagnetic waves. So, for example, light or electricity. Electricity, when we were talking about it, we said it travelled from electron to electron. Some people think of it as the electrons actually moving, but it's not. It's actually the energy travelling from an electron to an electron to an electron. Same thing happens with other waves, such as mechanical waves. The examples we have for that are sound waves and water waves. And there's three types of mechanical waves: transverse, longitudinal, and surface waves. So the analogy we have is water waves. So if you have a look at the diagram, this is kind of like a water wave. And what happens is the wave travels along here and it's basically moving in this direction. So each of these peaks is moving across, and when it gets here, then it has to turn around and go back. We'll talk about that later. But a transverse wave moves in a direction perpendicular to the direction that the wave moves. So the wave's moving this way and the particles of the medium move up and down. So this is kind of like water waves. A longitudinal wave is more when the wave moves in a direction parallel to the direction that the wave moves. So this way, the wave is moving this way and the particles are moving back and forth. So there's a compression and a rarefaction. And these are examples of these are pressure waves, which is an example of a sound wave. A sound wave is a longitudinal pressure wave. The other one we talked about was a surface wave. We're not going to discuss that at all, except to say that instead of going up and down or back and forth, it goes round and around. So it's more of a circular motion. The wave has several properties which I'm sure that you've covered before, but we'll review it anyway. It has a sinusoidal shape, and the shape has a certain amplitude. The amplitude is basically from this equilibrium or rest position through to this point here, the crest. So the amplitude refers to the maximum amount of displacement. It's really the distance from the rest to the crest or from the rest through to the trough. In the diagram, the amplitude can be measured as the distance of the line segment that is perpendicular to the rest position and extends vertically upward. We also have the period, which is the time for one complete cycle. And the distance for one complete cycle is the wavelength. So the distance travelled from crest to crest, or from trough to trough, or from any point on a wave to a corresponding point on the next cycle of the wave is the wavelength. The frequency is the number of wavelengths per second, or the number of cycles per second, and it's measured in hertz or per second. And there is a relationship between the frequency and the period, which we've looked at before with simple harmonic motion. There's an inverse relationship. So the number of cycles in 1 second is equivalent to 1 over the time required to complete one cycle. The speed of the wave is therefore how long it takes, the distance, of the time that it takes, the period. The wavelength times the number of the waves per second is the frequency. We don't normally use this one where it's the wavelength over the period, but we often use this one, V equals F lambda. Lambda is your wavelength. So looking again at this picture, you can see our crests and our troughs, our wavelength, our period, our frequency is how many goes in per second, our equilibrium position, which is this part here, all of the descriptions of the wave. A travelling wave is one that's not confined to a given space, so it's something like an ocean wave which keeps going and going and going. But if you have a wave that's in a fixed area, like in the example when we're looking at the string where you move up and down, then it's going to reflect off a boundary and it's going to interact with the other waves and it's going to cause an interference pattern. And we're going to cover interference in a lot more detail a bit later, but what the interference causes here is a stable interference pattern. It's called a standing wave. So you can see here we have a standing wave here, and these peaks are called antinodes, they're the crests, and the parts that aren't crested, whereas stationary parts are called nodes. So we might call them stationary nodes. And this standing wave occurs when the frequency of a wave or a set of waves is ideal for a particular area. And this occurs quite often with sound waves. So sound waves, as we said, are longitudinal pressure waves. Louder sounds have louder amplitudes. See, a higher amplitude. Quieter sounds have smaller amplitudes. And what we actually hear is basically our ear hears this compression and rarefaction of the air particles. So it's a pressure wave that our ear hears. And we actually hear it as in terms of pitch. And pitch is related to the frequency. A high pitch corresponds to a high frequency, so lots of wavelengths per second. Whereas a low pitch sounds corresponds to a low frequency. So learning how to use these diagrams is a really good way of describing how loud or soft something is, or what frequency it is, whether it's high pitch or low pitch. Well, the speed of sound is dependent on the medium. So in a solid, it's greater than in a liquid, and it's greater than in a gas. And in air, it's usually 331 meters per second, and there is a temperature coefficient, so it depends on the temperature. And so it would depend on what sort of day it is as to how the speed of sound works, which then affects the frequency. So this is why instruments have to be tuned constantly. So let's go back to this standing wave, because it's a really good description of how things work in strings. So the wavelength of a standing wave for any given harmonic is related to the length of the string, and also the vice versa. So the harmonic frequencies can be found as a function of our fundamental frequency. In this case, we're looking at a guitar string. So there's two nodes, which are two fixed points, which is the point up at the top near the frets, and a point near the other bit of the guitar. And you can see that the lowest harmonic is when that is half a wavelength. So if you add that up and then continue, that would be one full wavelength, but there's only half a wavelength within that length. So our first fundamental frequency down here is related to the velocity divided by that wavelength, which was 2L, so it would be V over 2L. Our second frequency is our harmonic, so this is the second frequency that can be related to this guitar string, and you can see that it's a complete wavelength, so 2 on 2L, or it's just L. So in this case here it would be V over L, but you could also see this was 2L and this was 1L, so our second frequency is related to our first fundamental frequency just by this factor of n, so the harmonic number. So if we follow this through for 3, you can see, okay, it's 3 times the fundamental, and for n, our frequency of any harmonic is n times that fundamental frequency. So how are we going to do these problems? What we're looking at is the speed of waves in a particular gas string. Remember that the speed was greater in a solid, and speed in a string is related to the tension, how tight it is, and also the mass per unit length. So determining the fundamental frequency of a string if its length is 76.5. Well, remember the fundamental frequency for a string was twice times the length, well, the fundamental wavelength, twice times the length. So if we use the table and the problem solving technique above, we can find that the fundamental frequency is when the wavelength is 2L. So the frequency is velocity over 2L, or 425 divided by 2 times 0.765. So note that has to be converted into meters, and that gives us a frequency of about 278 Hz. So what was this problem solving strategy? This is basically looking at where you've got a length of string and you convert it into the wavelength. That's the first step. Make sure that you can know either the length or the wavelength, and you work out what those are. From the wavelength you can work out the frequency, because you know V equals F lambda. You can also work out the speed of the wave. So basically there's this conversion here, and from wavelength you can work out any of these things. So What other types of musical instruments can we look at? Pipes. So we look at this open pipe, such as a flute, and you can see here we have no nodes here. That's an antinode there, but we have one node in the middle. And our length here, again, is about half a wavelength. So if we continue there and then down again, that would be a full wavelength. So that means our wavelength is 2L, and our frequency again is V over 2L, which is our fundamental. So this open pipe has the same set of harmonics as a set of a string of the same wavelength, except for the fact that the string would have a higher velocity because it's a solid, whereas an open pipe has the velocity of sound in air. How would we use this open pipe? The speed of sound in air is found to be 340 meters per second. What's the fundamental frequency of an open air column that has a length 67.5? So just like in the string, it has a fundamental frequency when the wavelength is 2L. So using that wavelength, we find that our frequency is 252 Hz. For a closed pipe, this is a bit different. So one end is closed and the other end is open. An example of this might be a clarinet. And you can see if you try and figure out how many wavelengths are in there, you've got to go 1, 2, 3, 4. Okay, it's going to be 4 lots of the length would make one wavelength. So that means this length is a quarter of the wavelength. So our fundamental frequency is the V over 4L. That's our fundamental. And then we look at our second harmonic, or the second, and you look here and you go, okay, well there's a node, antinode, node, antinode. Well, that's actually not quite one wavelength. If we go, we need to go another kind of a quarter of a wavelength. It's only 3/4 of a wavelength in there. So if you look at that, that means the wavelength is 4/3 of L, which is about 1/3 of your fundamental, which means that when you look at your fundamental frequency, it's 3 times this first harmonic here is 3 times our fundamental frequency. And in fact, what we find is that this is actually called the third harmonic, the first overtone or the third harmonic. Same thing goes when you go a little bit further, you go to the fifth harmonic. So we've got odd harmonics here, not 1, 2, 3, 4, 5. We only have 1, 3, 5. Let's have a look at the problem. The speed of sound waves in air is 340. Again, a pipe that has 67.5, but now it's a closed pipe, so the same length, closed. And if you use only the odd harmonics, then the fundamental is when the wavelength is 4L. So this would be 126 Hz. So something interesting, if we're only using odd harmonics, then we're not going to get 2 times this fundamental frequency, we're only going to get 3 times. So the next harmonic, the third harmonic, would be not 252, it would actually be 378. That would be 378 Hz for the next harmonic that you could have in a closed pipe. So that's just a short description of sound waves. We'll do a lot more in class, and we'll use a lot more technical language. We'll do a lot more problems, but that gives you a good indication of what we're going to be doing this week.